Hey guys, Mr. McKinney here, just doing our 9.4 video series on the fundamental theorem of calculus, the anti-differentiation piece. So basically, the idea that derivatives and integrals undo each other. The vast majority of this is review. Really, I think it's all review. So it'll go fairly quick. So one piece of the fundamental theorem of calculus says that as long as little f is continuous on this interval, then the antiderivative, or the integral of it, has a derivative at every point. Now, this is just a convoluted way of saying that derivatives and integrals undo each other as long as certain things are in the right place. So you need to have a constant as the lower limit. You need to have a variable as the upper limit, or a function, and we'll get into those later on. But the variable should be on the upper limit. And that variable on the upper limit needs to be the same as the variable that we're taking the derivative with respect to. If these variables don't match, then the fundamental theorem of calculus doesn't apply. And then whatever variable you have on your function on the inside should match the variable of integration. This variable should be different than the variable that's on top. So if you're ever creating an equation like this, make sure you use a different variable here than what you did on top. But as long as you have a constant on the bottom, and this variable matches, and this variable matches, then you just plug in the variable on the top, and you are done. You're not actually taking the integral, you're not actually taking the derivative, you're recognizing the fact that derivatives and integrals undo each other. So let's do a couple of examples. So capital F is equal to the integral from 0 to x of t cubed plus 2t dt. I want to find f of x, which is the same as capital F prime of x. So little f of x would be capital F prime of x, which would be the derivative with respect to x of the integral from 0 to x of t cubed plus 2t dt. So now I'm just making sure that everything matches. I've got a constant, this variable matches, and this variable matches. So everything's in the right place. So all I have to do is plug in x anywhere that I see t. So my answer for little f of x is going to be not t cubed, but x cubed, and then not 2t, but 2x. And I'm done. So as long as you have a constant on the bottom and then the variable on top, you're just going to plug in the variable if you're taking the derivative of an integral. So derivatives and integrals are just going to cancel each other out. All right, you guys do these two and then check your work. All right, let's see how you guys did. So on the first one, everything's in the right place. So you're literally just plugging in x. So instead of cosine of t, the variables will switch and it'll be cosine of x. So that's it. The second one requires one extra step. You need to have the constant on the bottom and the variable on the top. So I need to flip the limits. And there's a property for definite integrals that says you can flip the limits if you put a negative out front. So I just need to flip the limits and put a negative out front. Then I can apply the fundamental theorem of calculus, plug in x. So I can either write it as negative and then times sine of x minus tangent of x, or I can distribute that negative and make it negative sine x plus tangent of x, or I can switch the order and make it tangent of x minus sine of x. This would likely be on the multiple choice portion, so you'd have to look and see which of these options were there. Any of these are acceptable on the free response portion. All right, so that was the basic version of FTC anti-differentiation. Sometimes you're going to need to apply the chain rule. Basically, if you take the derivative of a composite function, then you take the derivative of the outside function and multiply by the derivative of the inside function. That's the regular old chain rule. And then we're doing the exact same thing here. So if you don't just have x, but if you have a function of x on the top, you plug that whole function in just like you would before. So f of that whole function, and then you multiply by the derivative of that function. It's really just a different version of the chain rule. So let's look at a couple of examples. So I want to find little f, starting with capital F. So again, I'm going to be taking the derivative, but I have x cubed on top instead of just x. So capital F prime would be equal to little f, which would be equal to the derivative with respect to x, integral from pi over 2 to x cubed of cosine of t dt. Everything's in the right place. This variable matches. We have a constant, and this variable matches. So now I need to plug in x cubed anytime I see t. So instead of cosine of t, it's going to be cosine of x cubed. And then I need to use the chain rule. So I need to multiply by the derivative of x cubed, which is 3x squared. I could leave it like this. I would likely move the 3x squared in front, so it's obvious that the 3x squared is not inside the cosine. Either of these is acceptable. All right, so just use the chain rule. If the function on top is more than just x, multiply by its derivative at the end. Now this one's incredibly similar, but instead of t, we have cosine of 2t. Everything works exactly the same. I just need to make sure I plug in x cubed for t. So it's going to be 2 times x cubed when I plug it in, and then I have to do the chain rule. So little f of x is going to be the derivative with respect to x of the integral going from a constant to a function. All right, so everything's in the right place. So I literally just need to plug in x cubed and then multiply by the derivative. But make sure you're only plugging in an x cubed for t. So there's still going to be this 2. So I'm going to have cosine of 2 times x cubed, and then the derivative of x cubed, which is 3x squared. So little f of x would be 3x squared cosine of 2x cubed. So whatever is in the original equation needs to stay there. The only thing that changes is the variable. Replace it with either the new variable or the new function, and then multiply by the derivative of the function if you have to use the chain rule. All right, okay. Take a second to work on these two examples, and it's going to reference some stuff that we did back in first semester, or back in Unit 7 actually, which was this semester. All right, let's see how you guys did. The first one, just plug in sine, so square root of sine, and then multiply by the derivative of sine, which is cosine. I would probably rewrite it with the cosine out front, so it's obvious that the cosine is not underneath the root. The second one involves a few more steps. So we need to have a constant in order to apply FTC. X and x squared both include a variable. So our first step is to split it up. You can put whatever constant you want in the middle. Doesn't matter what constant you use. I just picked 0 because that's easy. Now this one is set up to go, so I can plug in the x squared and then multiply by the derivative of x squared. So secant squared of x squared times 2x. Before I can use FTC on this first piece, I need to flip it so that the constant is on the bottom. So it's going to be negative, and then I'm just going to plug in x here. So it'd be negative secant squared of x plus secant squared of x squared times 2x. And then I rewrote that the way that you would likely see it on a multiple choice question. So negative secant squared of x plus 2x secant squared of x squared. All right, well that's it for fundamental theorem of calculus, antidifferentiation. The vast majority, or really all of this, was review. So hopefully this was a good refresher. We're gonna look at one other version of FTC, but I'm gonna put it into a separate video. So I'm gonna stop here. Hope this was helpful.